Welcome to the presentation of our final year project, Enhancing Behavioral Biometrics with IMU Data. In this presentation, the outline is as follows. We will go through the introduction, problem statement, objectives, related work, ICAC conference paper, IJCB conference paper, prototype, discussions, publications and achievements, study contribution, demo and references. First, let's go through the introduction. In the modern day world, the usage of mobile devices, especially smartphones, rapidly increase day by day. People confide their personal data, rely on vital applications such as banking, health, education, more and more on these devices. This increases the security concerns in smartphones. On the other hand, these are easily shareable or lost. If these are taken to by the wrong hands, high amount of damage can be caused for the owner, exposing their privacy. This is why a high level of security is vital in the mobile phone industry. The solution for a higher level of security is behavioral biometrics based continuous authentication, also known as CA. Why CA over existing authentication methods? I will explain in the coming slide. However, in order for CA to become a reality, it needs to have a higher discriminativity to perfect both usability and security aspects. To achieve this, we are proposing IMU enhanced behavioral biometrics based CA. Before speaking about continuous authentication, let's first see what authentication is. As a definition, authentication is the process of determining whether someone or something is in fact who or what it says it is. Authentication for smartphones can be categorized into two categories based on their authenticating behavior. The first one is one-time authentication or static authentication, and the second one is continuous authentication. In one-time authentication, the user has to perform a specific action to authenticate and use the device. After that, no authentication is done until the device is locked again, or we can say throughout the session, except for some application level authentications. This is also known as session-based authentication. In continuous authentication, on the other hand, there is no specific task the user has to follow to authenticate himself. The authentication is continuously happening under the hood. Now let's talk about existing traditional authentication systems. These can be categorized into two types. One is knowledge-based and the other one is biometrics. Examples for knowledge-based systems are password, PIN codes and patterns. These are vulnerable to guessing, smudge attacks and spoofing. Biometrics can also be categorized into two as hard biometrics and soft biometrics. Hard biometrics such as fingerprint and DNA are very unique to each user and very much discriminating. The issue in this, however, is that these are still one-time authentication systems. The other biometrics is soft biometrics, also known as behavioral biometrics such as voice, gait and keystroke. These are not very much discriminating. Therefore, they are yet to become reliable authentication systems. Now let's look more on behavioral biometrics, also known as soft biometrics. When using smartphones, each person has unique traits such as their typing behavior, the use of touch gestures such as tapping, swiping and scrolling. As a definition, behavioral biometrics can be defined as the field of study related to the measure of uniquely identifying and measurable patterns in human activities. Behavioral biometrics are used in continuous authentication. Some examples are keystroke dynamics, which is the typing behavior of the user, and touchstroke dynamics, which is the user's behavior of touch gestures. Although continuous authentication solves the problems in knowledge-based authentication and hard biometrics, the discriminative power is yet to be improved to be used as reliable and usable authentication systems, which brings us to the problem statement. Every modern-day smartphone contains an inertial measurement unit, also known as IMU. IMU contains of accelerometer, gyroscope, and magnetometer. As I've said previously, the discriminative powers of behavioral biometrics should be improved for them to become everyday authentication systems. These IMU data can be used in increasing the discriminative powers of behavioral biometrics. Therefore, our problem statement is increase the discriminative power of behavioral biometrics using IMU data for continuous authentication systems. Now let's take a look at our research objectives. The first objective of our project is to explore existing behavioral biometric authentication systems using continuous authentication evaluation metrics. The second one is to develop a novel model to incorporate IMU-based features to enhance the discriminative power of behavioral biometrics. The third objective is developing a prototype for CA system for smartphones to showcase the proposed model.
Let's see an overview of related work in our research. For clarity, we divided those into three parts. First one is keystroke only continuous authentication systems. As you can see, initial works was carried out using traditional classifiers like random forest, k-means and snable, and support vector machine. In 7, they present a comparison between 7 different classifiers and concluded GPC performed well among those. In 14 and 15, they used deep learning techniques with LSTM and transformers. The second one is CA system which use both keystroke and touchstroke. In the latest study mentioned here, they use multi-stream RNA. Last one is keystroke, touchstroke plus IMU data combined CA systems. In here, all the works are gone with LSTM multimodal approach. They train unimodal for each modality and then detect score level fusion to get results. In here, we can see how CA systems have grown over the years. First, they used traditional ML classifiers and then moved to deep learning, which is LSTMs, and most recently to transformers. As a summary, for dataset, IMU, HMOC, and ALTO dataset were mostly used, and latest multimodal are used LSTMs, but none of these are not used latest deep learning approach, which is transformers. Also, all these experiments were evaluated through only traditional evaluation matrices such as EER, FAR, but none of these mobile CA systems are evaluated using continuous evaluation matrices, even though they are continuous authentication systems.
Now let's look at our key research task. Our first research task was to explore existing behavioral biometric authentication systems using continuous authentication evaluation metrics. This led to our first conference paper, Re-evaluating Keystroke Dynamics for Continuous Authentication, which we published in ICAR 2023. The second task was to develop a novel model to incorporate IMU-based features to enhance the discriminative power of behavioral biometrics. This led to our second conference paper, Behaveformer, a framework with spatio-temporal dual attention transformers for IMU-enhanced keystroke dynamics, which was accepted for IJCP 2023. Now let's look at our first research paper, Re-evaluating Keystroke Dynamics for Continuous Authentication. First, let's take a look at the research process we followed for this paper. First, we identified the datasets and models to be developed. We chose AltoDB as our dataset. Next, we developed 6 models. 3 models included deep learning approaches and the other 3 included traditional ML methods. Next, we evaluated all these models with a traditional evaluation metric. The metric we have chosen is EER, which is the equal error rate. EER is the location on a ROC or dead curve where the false acceptance rate and false rejection rate are equal. Next, we do our evaluation with continuous evaluation metrics. We have chosen 4 evaluation metrics, which are usability, TCR, FRWI, and FAWI. The definitions for those evaluation metrics will be covered in the coming slides. Finally, we analyzed all these results. For the features, in addition to hold latency, ASCII code, we use 3 diagram features, which are interkey latency, press latency, and release latency. Now let's go through the definitions of continuous evaluation metrics we use in our study. These evaluation metrics have been used for computer continuous authentication systems but not for mobile continuous authentication systems. First, let's look at usability and false reject first interval. Usability is the fraction of the total time that the legitimate user is granted access to the protected resource. High usability is vital for an authentication system. False reject first interval is the longest time interval over which a legitimate user might be falsely rejected and marked as an imposter. A low FRWI is important for better usability. Next, let's look at false accept first interval. False accept first interval is the longest time interval over which an imposter can be falsely accepted as a legitimate user. FAWI evaluates an important security aspects, and a FAWI should be minimized as much as possible. Time to correct reject is the interval between the start of the first action taken by the imposter to the time instant that the system correctly rejects him. TCR should also be low for better security. As mentioned before, we use AltoDB as our dataset. It contains data of around 260,000 users, each having 15 sessions. The diagram below shows the method we followed for enrollment and verification. In the enrollment phase, users' key event data is used to create a feature embedding which is stored in a signature database. In the verification phase, users' key event data is again used to generate a new feature embedding. This new feature embedding is compared with the existing feature embedding, by which we determine if the user is legitimate or not. This slide includes the results of existing keystroke dynamics-based continuous authentication systems with respect to EER, which is the equal error rate. Since a lower EER indicates a higher performance, we can order the systems from best to worst as RFC, KNN, TypeNet, GBC, Typeformer, and HUMNet. This slide includes the results of existing keystroke dynamics-based continuous authentication systems with respect to usability. Since a higher usability indicates a higher performance, we can order the systems from best to worst as RFC, KNN, Typeformer, GBC, TypeNet, and HUMNet. This slide includes the results of existing keystroke dynamics-based continuous authentication systems with respect to TCR. Since a lower TCR indicates a higher performance, we can order the systems from best to worst as GBC, TypeNet, RFC, KNN, Typeformer, and HUMNet. This slide includes the results of existing keystroke dynamics-based continuous authentication systems with respect to FRWI. Since a lower FRWI indicates a higher performance, we can order the systems from best to worst as RFC and KNN, HUMNet, Typeformer, GBC, and TypeNet. This slide includes the results of existing keystroke dynamics-based continuous authentication systems with respect to FAWI. Since a lower FAWI indicates a higher performance, we can order the systems from best to worst as KNN, GBC, RFC, TypeNet, Typeformer, and HUMNet. This slide includes the results of an analysis we did for TypeNet using different keystroke sequence lengths and different enrollment sequences. As you can see, increasing the number of enrollment sequences has increased the results with respect to both traditional and continuous evaluation metrics. A keystroke sequence of length 70 has yielded the best performance with respect to EER, and it has shown the same behavior with most continuous authentication evaluation metrics.
Next, We are going to present the second research paper which covers the second task of our research. The title of the paper is Behaveformer, a framework with spatio-temporal dual attention transformers for IMU enhanced keystroke dynamics. In this paper, we developed a novel model to enhance keystroke dynamics continuous authentication by incorporating IMU data. We named this model as Behaveformer. As you can see in this slide, Behaveformer consists of two transformers called keystroke STDAT and IMU STDAT. Keystroke STDAT extract features from keystroke data, while IMU STDAT extract features from IMU data. Finally, feature embeddings from both transformers are concatenated using a concatenation layer to generate the final composite feature embedding. In this slide, you can see the high-level architecture diagram of the modified transformer which is used in the Behaveformer model. We named this model as Spatio-Temporal Dual Attention Transformer (STDAT). This transformer is somewhat different from the vanilla transformer. Those differences are we have used Gaussian range encoder as the positional encoding system, which can embed position details considering ranges of positions. As the attention module, we used two main components called temporal multi-head attention and channel multi-head attention. Temporal multi-head attention is responsible for calculating attention scores through the temporal axis, while channel attention calculates attention scores through the channel axis. Finally, complete attention module computes total attention scores of all items in an input sequence. Then, we have used a 2D convolutional neural network to extract features from attention embedded input sequence by considering both temporal and channel axes. Finally, fully connected neural network is used to generate the final individual modality feature embedding. In this paper, we followed a pre-processing and feature creation process before giving data to the model. As you can see in this slide, we extracted 10 features from keystroke data by considering both digrams and trigrams. Digrams means consecutive 2 key events and trigram means consecutive 3 key events. For IMU data, we calculated first derivative, second derivative and fast Fourier transform. Finally, we synchronized all 3 types of IMU data to generate each sequence. We have used 3 datasets in this paper. L2DB is a large-scale dataset which consists of 260,000 users' data. HMOGDB is a small-scale dataset which consists of 100 users' data. HumiDB is a medium-scale dataset which consists of 599 users' data. L2DB only contains keystroke data while HMOG and HumiDB contain both keystroke and IMU data. This slide represents the enrollment and verification protocol that we used in this paper. This is exactly similar to the previously explained protocol. Next, I'm going to present the results of experiments related to this paper. This slide presents the performance of Behaveformer across datasets. When we consider the keystroke only case, the best results were achieved through L2DB dataset. In keystroke plus IMU case, the best results were achieved through HumiDB dataset. When we consider HMOG and HumiDB results in both cases, we can identify there is a significant results improvement in keystroke plus IMU case. With that, we can state that after incorporating IMU data with keystroke data, performance of the model is improved. This slide presents the dead curves calculated for different combinations we considered in Behaveformer. In both graphs, red graph represents the keystroke only Behaveformer model and blue graph represents keystroke and IMU Behaveformer model. When we consider the HMOG graph, in most of the cases, blue graph is below than the red graph. When we consider the HumiDB graph, there's a clear gap between two graphs and blue graph is always below than the red graph. From that, we can conclude after incorporating IMU data with keystroke data, performance of the model is significantly improved. This slide presents 2D graphical visualization of the latent space through TS Sydney considering 10 subjects. As you can see, in most of the case, there's a clear difference between each clusters in these 3 graphs. Also, when we consider the Silout scores, which measures the goodness of clustering, we can identify that all scores are greater than 0.5. Therefore, the model can differentiate users by generating set of unique features. In this slide, we will present the comparisons of our L2DB Behaveformer model with 4 best state-of-art keystroke models. Here, black graph represents the keystroke-only Behaveformer model. You can identify that in all metrics, our model achieved the best results outperforming other state-of-art models. This slide presents the comparison of HMOGDB Behaveformer model with 6 best state-of-art models. Both keystroke-only and keystroke plus IMU cases are included in this graph. Black graph represents the keystroke-only Behaveformer model and red graph represents the keystroke plus IMU Behaveformer model. According to the results, in most of the cases, our model achieved the best results outperforming other models. Also, when we compare red and black graphs, red graph is achieved the best results. With that, we can conclude after incorporating IMU data, performance of the Behaveformer is significantly improved. Same graph is presented in this slide also with a different dataset HumiDB. Similar to previous graph, in most of the cases, our model achieved the best results outperforming other state-of-art models, and red graph achieved the best results. As an additional experiment, we checked whether the behavior model is supporting transfer learning. According to the results we received, you can identify that after using the transfer learning, model performance is increased than without transfer learning case. Therefore, behavior can utilize to get the advantage of transfer learning as well. In this slide, we will present the results related to the ablation study which was conducted to find the best subset of IMU data combinations. We conducted the ablation study for both HMOC and HumiDB datasets. This slide presents the HMOC results and next slide presents the HumiDB results. From this experiment, we identified that the best results can be achieved when we use all three types of IMU data together with keystroke data.
In the final phase, we have built a prototype to showcase our model performance. And this is the high-level architecture of prototype. It consists of three main parts, which are Android environment where our Flutter mobile app running, then Python environment where our Torch server up and running, and smartphone storage to store enrollment signatures. The process is, first user must enroll himself in the system, entering keystrokes. Then these keystrokes go through the enrollment handler and model handler to preprocessing. Then those preprocessed data fetch into model and it generates enrollment signatures and is stored in the smartphone. Then in the verification phase, user also enters the keystrokes. These keystrokes are also gone same as previous to model and it generates verification signatures. And in the authentication unit, we compare the enrollment and verification signatures. According to that, system predicts whether it is same person means legitimate user or an imposter user. These are the Flutter mobile app screens. First one is enrollment screens where user can enroll user keystrokes, simply typing and then pressing enroll. Also users can reset enrollment. The second screen is verification screen where user can type and see confidence score real time to know whether user is legitimate or imposter. Now let's see conclusion what we got from our research. From our first paper, we saw behavioral biometric based continuous authentication system should be improved with respect to both traditional and continuous evaluation metrics. From our second paper, we concluded that fusion with IMU data has a significant effect on the performance of continuous authentication systems, and effectively leveraging IMU data for behavioral biometrics has the potential to serve as a promising avenue for successful continuous authentication in the future. As future works, we can continue this research to use touch stroke dynamics to improve the model performance. As our publication and achievements, we published a paper called Re-Evaluating Keystroke Dynamics for Continuous Authentication and won Best Paper Award in HCI Computer Vision Streaming ICAR 2023. Also, we wrote another paper called Behavior a framework with spatial temporal dual attention transform for IMU enhanced keystroke dynamics, and it accepted in IJCB 2023 conference. Now, let's see how our prototype works.
As the first step, legitimate user should enroll to the authentication system by entering any text using the enrollment section of the prototype. Next, I will move to the verification section of the application after the enrollment completed. Here, as the first verification, legitimate user will enter a different text and check whether the system is identified the legitimate user correctly. you can see, when typing the legitimate user, confidence score is greater than 50. That means system can identify the legitimate user. As the next verification, imposter user who is different from legitimate user will enter a text and check whether the system is identified the imposter user correctly. As you can see, when typing the imposter user, confidence score is lesser than 50. That means system can identify the imposter user.
If you need more details on this area, here is our reference. And thank you for your undivided attention.